Let's use our other, we already did acetic acid, so let's use our other super common weak acid. So a buffer system can be a weak acid and a salt of its conjugate base. So remember, its conjugate base is going to be whatever it looks like after it gives up an H and a plus, which is F minus, and we're going to give him either a sodium or a potassium every single time. So the sodium, we're going to put this in water. The sodium is a spectator ion, so we can ignore it. Remember, it's the double arrows because this is a reversible reaction. And here's where we stand. So this is what's really going on in a buffer system. And the crucial thing about buffer systems is that they can counteract the addition of acids or bases. So let's see what it looks like. If I add acid in the form of a strong acid, remember something like HCl, HNO3, those are strong acids, meaning they dissociate completely. Their anions are neutral. Therefore, they're just going to be spectator ions in solution. So when we add a strong acid, we're really just adding H+. H+ is going to come in, and he's going to seek out that weak base. When we say he's a weak base, we mean that he will bind with H+. He will accept the proton that is H+. When he accepts the H+, the pH does not plummet like it would otherwise. Instead, he forms a molecule and we get more weak acid, which does not plummet the pH. If we add OH minus, this guy, in the form of a strong base, these are just some examples of strong bases. Their cations in this case are neutral, so they are spectator ions. He's a minus, so he's going to seek out an H+, so he can pluck an H+ off of this weak acid and form more water, and then leaving behind more F-. So OH-, if you added it to a non-buffered solution, would spike the pH way up immediately. Instead, he will consume some of the weak acid and form more conjugate base. Now, each buffer system is different in that they protect against different pH ranges. So what is the pH range? Well, first thing we have to do is look up the Ka. The Ka for hydrofluoric acid is 3.53 times 10 to the minus 4. So in order to understand the range at which this will protect at, we have to calculate the pKa, which is the negative log of the Ka. So in your calculator, you plug in negative log of 3.53 E minus 4, and the pKa in this case is 3.45. So the range is 3.45 plus or minus 1. That means that this buffer system will protect pHs in the range of 2.45 to 4.45. That's how acidic buffer solutions work. Now let's talk about basic buffer solutions. Those would be made from a weak base and a salt of its conjugate acid. So NH3 will act like a base and accept a proton, which is an H and a plus. So NH4 plus, or the ammonium ion, would be its conjugate acid. We'll add a spectator ion there, and that's a salt that we could pick. So what we got going on here is the weak base, when put into water, will accept a proton and leave behind OH minus. That's the definition of being a base, is to leave behind that OH minus. Again, if we add H plus in here in the form of a strong acid, the H plus and the ammonia will find each other. So instead of plummeting the pH, instead we will form more ammonium ion, and it won't affect the pH nearly as much. If I add OH minus in the form of a strong base, he is going to seek out the weak acid and pluck off that H plus to form more water. And then he will leave behind more weak base. This is how buffer systems work. In order to figure out what pH range it protects in, you look up the Ka for the ammonium ion, which is 5.64 times 10 to the minus 10. So in your calculator, to get the pKa, it's negative log of 5.64 times 10 to the minus 10 for a pKa of 9.25. Therefore, the range would be 8.25 to 10.25 that it would protect the pH. So double check your lab that you did not make some careless mistakes or rookie mistakes, because we're not rookies anymore. You did not put two anions together. You did not put two cations together. And you understood what was going on when you put the strong acid and strong base in there.